We now begin our investigation of consumer theory, starting with the basic building blocks of preferences and utility. When an individual is presented with a pair of choices, A and B, if they were to say, I choose A over B, we can say that A is preferred to B. This preference relation, it's written as a greater than sign, but with squiggly lines, tells us that this person likes A better than B in any conceivable scenario. The preferences that people actually exhibit can be all over the place. I don't really have to follow any rules or patterns, but in order to conduct economic analysis, it's typically a good idea to impose a standard set of axioms. The first of these assumptions is completeness, which says that if I have a pair of alternatives, then either A is better than B, or B is better than A, or I find A and B to be equivalent. Notably, this excludes the possibility of saying that I'm not sure, I don't know, or possibly sometimes I pick A and then sometimes I pick B. The second axiom is transitivity, which says that if A is better than B and B is better than C, then A is better than C. This assumption prevents people from having cyclical preferences. So you couldn't have A is better than B and B is better than C, but C is better than A, so it goes around in a circle. Finally, we assume that preferences are continuous. Now, without going into all the math, what this basically means is that there's no special quality attached to a particular outcome. So if we can get close enough, then it's good enough. This assumption is important because it's going to allow us to represent these preferences with a continuous utility function, and with a continuous function, we can do calculus with it, which would not be possible if there were discontinuities or jumps. If these three axioms of completeness, transitivity, and continuity hold, then we can rank all the possible outcomes that represent these rankings with the utility function. So A is preferred to B if and only if the utility of A is higher than the utility of B. These outcomes, A and B, could potentially be anything. But for our purposes, for consumer theory, we're going to assume that the utility functions are defined over bundles of goods. So if you have n goods, and x1 through xn represent the quantities of each good, the utility is going to be a function of these quantities. It's important to note here that the utility function only exists as a representation of the consumer's preferences, and therefore it's ordinal, which means that the number just tells us which bundle we like better. It doesn't tell us how much we like it over the other one. Furthermore, utility cannot be compared between people, which allows economists to conveniently dodge any questions about whether taking something from one person and giving it to another person would be a good thing overall or not. In a consumer choice context, utility is a function of the consumption of goods, but different people might evaluate the same bundle differently depending on a number of internal and external factors. As there's no objective measure of how useful any particular good is, utility is ultimately determined by individual psychology. However, this doesn't mean that each consumer independently arrives at a separate valuation, as influences from others can also alter your perception. Utility should also not be viewed as unchanging and static, as your preferences can change over time depending on personal experiences or of events that affect society around you. While it would be possible to construct a utility function that depends on every possible factor that might affect a person's happiness, this is too complex to be useful, and in general, we're only going to include those arguments that relate to the problem we're studying. Everything else can just be held constant by the ceteris paribus principle. Since we're typically talking about utility as a function of bundles of goods, we're going to take these quantities as arguments. If we just have two goods, we can just call them X and Y. Other models might look at utility as a function of wealth, or utility as a function of consumption and leisure, or utility of consumption at different points in time. So it all depends on the problem that we're studying. One assumption we will typically make is that more of something is always better than less, which anybody who has ever eaten too much ice cream and gotten a brain freeze might dispute, but is close enough for our purposes. This means that if we have a plot showing all the bundles of X and Y that we can consume, then relative to the bundle X star, Y star, everything to the lower left will be worse, while everything to the upper right will be better. Now the two areas marked with question marks are what we're interested in, since we will either have less X and more Y, or less Y and more X. Now whether this is better or worse depends on how the consumer views the trade-off between these two goods. To express this trade-off, we're going to define an indifference curve as the set of all points with utility equal to some constant value. So everything on this indifference curve has the same utility. If you've ever seen those contour maps with lines showing areas of equal elevation, this is kind of like that. So our indifference map is going to consist of multiple indifference curves, each representing a different level of utility. Since we assume that more is always better, the slope of the indifference curve is always presumed to be negative. Since if we're gaining more X, then in order to stay at the same level of utility, we would be losing some Y. The negative of this slope minus dy dx is called the marginal rate of substitution. This tells me how many units of Y I'm willing to lose in order to gain 1 unit of X while remaining at the same utility level. Looking at this graph, the bundles x1, y1 and x2, y2 both are on the same indifference curve and thus give the same utility to the consumer. As we trade y for x, as we move down the indifference curve, we can see that the slope becomes flatter and flatter, and thus the marginal rate of substitution has decreased. This means that at x2, y2, x has become less valuable relative to y compared to x1, y1, indicating that we have a diminishing marginal rate of substitution. Looking at this graph, we can see multiple indifference curves at different levels of utility. The utility level itself is not plotted on this graph, but we can assume that since more is usually better, utility should be increasing as we move up and to the right. Indifference curves have some additional properties that will be meaningful to our analysis. Two separate indifference curves can never cross, since by transitivity, this would mean that these are actually the same indifference curve. Indifference curves are also usually drawn curving upward, so the upper contour set, the area above it, is a convex set. So any 2 points that are above this indifference curve, the whole line connecting them is also going to be above the indifference curve. This is going to give us the property of diminishing marginal rate of substitution, which basically tells us that consumers prefer mixing. They prefer variety. They don't want to spend all of their money on one good. This diagram shows what happens when indifference curves cross. By the curve at U1, the consumer is indifferent between bundle A and bundle E. But then by the indifference curve at U2, they're also indifferent between E and B. So by transitivity, A and B should be equally good. However, we can see that since A has more of both goods than B, it should in fact be strictly preferred to B. This contradiction shows that indifference curves cannot ever cross under the assumptions that we've made. In this diagram, we see on the left side an indifference curve with a convex upper contour set. Since if we connect the bundles x1, y1 and x2, y2, this produces bundles that are all at least as good, and in this case, strictly better, than anything on the indifference curve itself. The indifference curve on the right does not have this property, as x1, y1 and x2, y2 both lie above the u1 curve, but the line between them does not. Convexity is a useful property since it implies that consumers prefer to mix. On this graph, we see that the midpoint between x1, y1 and x2, y2 lies above the indifference curve and is strictly better than both of them. This agrees with the usual intuition that people generally like variety. Suppose that we have two goods. We have drinks and hamburgers. And we have an individual whose utility equals the square root of x times y. To plot an indifference curve, fix the utility at 10. This is going to give us the implicit function y is equal to 100 divided by x. To find the marginal rate of substitution, which is minus dy dx, we can take this derivative directly. That would give us 100 over x squared here. This shows that the more drinks that we consume, the lower the marginal rate of substitution, and therefore the fewer the number of burgers we're willing to give up in order to get more drinks. This diagram shows the plot of this indifference curve. We can see that because of convexity, if we take points A and B, then their midpoint, C, is going to be above the curve. That implies that C is better than anything on the curve. People would rather consume a mixture of burgers and drinks rather than only burgers or only drinks. If we have an indifference curve fixed at some utility level k, we can apply the implicit function theorem. So dy dx is going to be equal to minus ux uy. So the partial derivative with respect to x, which is the marginal utility of x, and the partial derivative with respect to y, or the marginal utility of y. This means that the marginal rate of substitution, which is minus dy dx, is equal to the ratio of the marginal utilities. We typically assume that goods have diminishing marginal utility, so that as x increases, the marginal utility of x is going to decrease, and as y decreases, the marginal utility of y is going to increase, and therefore this whole fraction is going to decrease. However, the concept of diminishing marginal utility is actually distinct from the concept of diminishing marginal rate of substitution. Because when we're talking about diminishing marginal utility, we're talking about partial derivatives. And with partial derivatives, if we're looking at the partial derivative of u with respect to x, we're holding y constant and changing x. And if we're looking at the partial derivative with respect to y, we're holding x constant and changing y. When we're moving along an indifference curve, x and y are changing simultaneously. So these concepts are similar but distinct. If u of x and y is equal to the square root of x times y, then the marginal utility of x is 1/2 times the square root of y over x, and the marginal utility of y is 1/2 times the square root of x over y. The marginal rate of substitution, therefore, is going to be equal to y over x. However, this is actually a lot easier to see if we take a logarithmic transformation. So we let u star equal log of u, which is equal to 1/2 log of x plus 1/2 log of y. U star x is just going to be 1 over 2x. U star y is 1 over 2y. And the marginal rate of substitution of u star is going to be y over x, same as for u. Intuitively, if we apply a logarithmic transformation to a utility function, all that does is change the utility level, but the utility level is not actually plotted on the indifference map, so the indifference map won't look any different, and therefore the slopes of the indifference curves will be the same, therefore the marginal rates of substitution will be the same. If we have a utility function x plus xy plus y, then ux is 1 plus y, uy is 1 plus x. The marginal rate of substitution is equal to 1 plus y over 1 plus x. Once again, we have diminishing marginal rate of substitution as we move down. If u is equal to the square root of x squared plus y squared, we can let u star be u squared. So that's just x squared plus y squared. That's another increasing transformation. And then u star x is 2x. U star y is 2y. So the marginal rate of substitution is equal to 2x over 2y, or x over y. Unlike in the previous examples, as we move down the indifference curve, the marginal rate of substitution actually increases. That means that this indifference curve is going to be curved down, facing the opposite direction as usual. What that means is that a consumer with this kind of utility function is actually going to be better off spending all of their money on one thing or another rather than trying to mix. One functional form that we're going to be seeing over and over again in this class, and not just in the context of consumer theory, is the Cobb-Douglas function. The general form is that the utility equals x to the alpha times y to the beta. These exponents are going to indicate how much the consumer cares about each good. Now, we can always normalize alpha and beta to sum to 1 just by taking a transformation, by taking this whole thing to the power 1 over alpha plus beta. So in general, we can write this utility function as u is equal to x to the delta, y to the 1 minus delta. We'll talk a bit about substitutes and complements a bit later on, but we can look now at two types of utility functions that are going to characterize perfect substitutes and perfect complements. If we have a linear utility function, alpha x plus beta y, then the marginal rate of substitution is just going to be constant. This means that the indifference curves are just going to be straight lines. As an aside, in economics, every line is a curve whether it is straight or curved. This means that x can be substituted for y at a constant rate no matter what the current quantity that we're consuming is of each good. If we have a fixed proportions utility function, so u is equal to the minimum of alpha x and beta y, then our indifference curves are going to be L-shaped. Because if alpha x is greater than beta y, or beta y is greater than alpha x, then consuming any additional amount of either good won't give me any additional utility. With this kind of utility function, I always need to consume the two goods in exactly the ratio where alpha x equals beta y, or else any excess is going to go to waste and not give me any benefit whatsoever. The constant elasticity of substitution, or CES utility, is going to look like this. This is something that we'll see repeatedly throughout this course as well. Leaving aside what elasticity of substitution actually means for now, if we have this functional form, then depending on the value of the parameter delta, we get each of the cases that we talked about before. So if delta is equal to 1, then we have linear utility, or perfect substitutes. As delta goes to 0, we have Cobb-Douglas. And as delta goes to minus infinity, we have fixed proportions, or perfect complements. This diagram shows what the indifference curves look like for each of the functional forms we just looked at. For the Cobb-Douglas, they're going to have the usual convex shape, so curving upward. For the linear utility, they're going to be straight lines. And for the fixed proportions, the curves will be L-shaped. So at the corners of the L's, they'll be in the right proportion. And as we go up or to the right, we're not going to gain any additional utility. For the CES utility, the curves look similar to Cobb-Douglas, but as we change the value of the parameter delta, they become more or less sharply curved. Each of the functional forms that we've introduced so far is homogeneous of degree 1, which means that doubling the quantities of each good will also double the utility. More importantly for us, this means that the marginal rate of substitution only depends on the ratios of x to y rather than on their absolute value. So for Cobb-Douglas, the marginal rate of substitution was y over x. Now, if we were to apply a transformation to this function, for example, if we let u star is equal to log of u, then we no longer have the property. But recall that if we apply a transformation, that doesn't change the marginal rate of substitution. So we're going to retain the property that the marginal rate of substitution depends only on the ratio of y over x rather than the levels. If we have a utility function that's not homothetic, such as, for example, x plus log y, then the marginal rate of substitution is going to be 1 over y, or y. Here, this does depend on the absolute level of y, not just the relative quantity y over x. So far, we've been looking at examples with just two goods, but we can do the same type of analysis if we had n different goods. So we just put the quantities of all of these goods as arguments in the utility function. The difference now is that rather than indifference curves, we're going to have indifferent surfaces in n dimensions. So that's not something we'll be able to draw very easily, but we can picture what they would look like. And instead of just a single marginal rate of substitution, which was minus dy over dx, we can define a marginal rate of substitution over any pair of goods. So we could say minus dx2 dx1. So this is how many units of x2 I would be willing to give up to gain 1 unit of x1 while staying at the same utility level. Now that we understand how preferences and utilities work, and we know some basic properties that are going to help us work with them mathematically, we're going to move on to thinking about how we can use them to solve the consumer's optimization problem.